LearningMeasure.tv, a science and engineering podcast with emphasis on measurement, brought to you by David Archer and LearningMeasure.com. Episode 39, Lewis Parker. Hello, I'm David Archer, owner of LearningMeasure.com and LearningMeasure.tv. LearningMeasure.com is a subscription-based training website, and you get, when you sign up, register as a student, you get 1 week free, and then it's $5 a month thereafter for access to all the courses. This week we're going to do something a little bit different. We're going to do an interview and a technical talk from somebody in our consultant network. You too can be a member of our consultant network. All you have to do is register as a student and then fill out a consultant profile on the consultant site. So this week we're going to have a conversation with Lewis Parker via iChat, and he's going to do a technical presentation as part of this podcast. All right, well, let's get to the interview.
Why don't you start out by telling me a little about yourself, your background, how you got into this?
Sure. So yeah, my name is Lewis Parker. My background is I got about 20 years in test and measurement. I started out in the military doing satellite communications, and then took on a second role into PMEL, or Precision Measurement Equipment Laboratory Technician. And when I got out, I found that I really liked that, so I continued on in that vein, pursuing a BSEE part-time while working full-time as an RF test technician. And so as I finished that up, I kind of went on in the role of managing calibration labs, application engineer for a couple of major test and measurement original equipment manufacturers. And then I decided to go out and start my own company that had a similar focus. So utilizing my background and finding people in my network that were similar to me. Over 20 years, you build up a pretty good network. So I contacted those folks and said, hey, what do you think about, especially those who were kind of semi-retired or were kind of starting their own consulting gigs anyway. And so what do you think about kind of networking together and doing a, focused test and measurement consulting and training company, and really helping folks to better utilize their test and measurement equipment, help them optimize their test setups, make measurements more accurately, efficiently, and effectively. And I got a number of people who were really interested and excited about that. So that's the beginning of test and measurement consulting.
Okay, you've answered several of the questions I was going to ask already. Is there any training or anything like that you're doing in the near future that you'd like to promote?
Yeah, I'm actually, I'll discuss a little bit here in the presentation, a little bit about probing. Working with one of my consultants is a 20-year veteran of designing and has a number of patents for probing probes for Tektronix. So we're working together to develop probably what will be an online webinar, potentially instructor-led. If a client is interested, we can come out and do some hands-on training and actually walk through some probing on their particular devices. But so I'll give a little taste of that here in this presentation. But that's something that we're definitely putting together right now, because we find a lot of clients struggling with probing issues, especially on high-speed buses and high-speed circuit design, where they're just not really making very good, and struggle a lot with making good oscilloscope probing measurements.
Okay.
So that's something we have coming up, a seminar on that.
Cool. So can you give me some of the details on that? How would you sign up for that?
Yeah, so if anybody's, we haven't actually announced yet a date, but certainly if anybody's interested, they can go to my website, www.tandmconsult.com, and it'll be on the slideware as well. And if you click on that and just say contact us, then just let me know you're interested in the seminar, the webinar, and we'll offer, it'll be a free webinar on specifics of probing. And I would imagine that'll be coming up here probably in the next couple weeks.
Okay, well, why don't we get started with your topic then?
All right, so today I'd like to talk a little bit about the real schematic, as I call it. So we'll talk a little bit about some of the parasitic capacitances and inductances that we find in circuits. That's my topic for today. So if we go on to my next slide there, I'll kind of get an overview of some of the topics that we're going to talk about. So today I'll cover the parasitic and parasitic capacitance and inductance of resistors, capacitors, inductors, and then we'll discuss a little bit about applying kind of that theory in a real-world application. And in this case, we'll talk a little about probing oscilloscope probes and the various kinds of probes and choosing the right one, that kind of thing, based on that theoretical discussion that we'll start out with. We can see that we have, as I mentioned, a number of different components in a typical diagram. And usually these schematic diagrams show resistors and capacitors, inductors, wires as ideal components. But in many cases, components can be considered as ideal. However, at high frequencies, the approximations are often no longer valid. The frequency-dependent departures from ideality are mainly due to parasitic capacitances and parasitic inductances. So electromagnetic theory dictates that any two conductors will have a capacitance between them, and that any conductor used for carrying current will have an inductance. At DC, inductive impedance is zero, a short circuit. So inductive impedance increases with frequency. Parasitic capacitance and inductance create reactive impedances that vary with frequency. So at DC, capacitive impedance is infinite. It's an open circuit, essentially. And capacitive impedance also decreases with frequency. So we see these very frequency-dependent kind of characteristics of capacitors and resistors that interact with each other. And this is part of kind of what's made people consider, RF and microwave in, a bit of black magic or voodoo, if you will. The fact that these ideal components begin to behave dramatically different at higher frequencies, and we'll talk more about what we mean by higher frequencies in the next few slides. So the parasitic impedances of components are present in every real component, but of course they're not really shown on a schematic diagram, which is what frustrates a lot of engineers, especially those who are more familiar with digital design, as they begin to get these higher frequencies and find these components behaving differently than they had anticipated. So if we go to the next slide, we'll begin with kind of what I call the true resistor. So here on slide 4, we see that real resistors have frequency limitations. As shown in this equivalent circuit here, the leads of a resistor create a capacitance that is in parallel to the resistance. The leads of the resistor and the resistive material itself create a series inductance. So both parasitic effects limit the frequency range of the resistor. For large resistors, the capacitance dominates the high frequency response, shunting out the resistance and reducing the effective impedance of the resistor. So although the resistance remains fairly constant, that is until it hits a corner frequency. That corner frequency is defined by the inverse of the resistance times the capacitance. You can see in my equation, or F equals 1 over R times C. So once we hit this corner frequency, we find that the resistor behaves differently, and it's worse for large resistances and for large parasitic capacitances. So for this reason, we typically try to avoid using high resistors or high resistive values at high frequencies, because it definitely will exaggerate this effect. Now, there are a few ways that you can improve performance in an instance like this. You can reduce the leads of a resistor. If you're actually using a resistor that has leads, you can shorten those and reduce the parasitic capacitance. If you're using surface mount resistors, you want to make sure that there are, typically rectangular blocks of resistive material with metal ends. And this in and of itself will reduce the capacitance greatly because they don't have extended leads. So you want to be careful about any kind of leads that you have coming off of the resistors that will, in effect, create a parasitic capacitance. So even for small valued resistors, the parasitic inductance dominates the high frequency response. So what does this mean? This means that we've effectively increased the effective impedance of the resistor. So especially with wire wound resistors, they have a notoriously high inductance. and cannot be used at high frequencies at all. So you're definitely starting to get away from discrete components and wire wound resistors at these higher frequencies. So as it turns out, 50 ohms being happens to be the most common characteristic impedance for use at high frequencies, and it serves as a good gauge for determining whether or not a resistor is very high or very low. So far I've kind of thrown out these pretty generic kind of terms, high frequencies, low frequencies. Let's try to quantify that a little bit. So one rule of thumb is a general but somewhat arbitrary guideline to use for selecting chip resistors is shown here in this equation. This rule of thumb, where F is the frequency of operation in hertz and R is the resistance in ohms. So if we take and divide that resistance in ohms by 50, and if we kind of look and see where it falls between these two values, then we know that that's generally a good value to utilize. If it's above that, it would be considered high, and beneath that, we consider it low. So again, of course, this is just a rule of thumb. It's certainly no substitute for measurements or simulation. So moving on to slide 5, and we talk a little bit here about the true capacitor. So all real capacitors have several parasitic elements, again, as we show here in our true diagram, if you will, of a capacitor. We see that the leads of a capacitor have inductance and resistance. There's also, in addition to that, the dielectric material between the plates do not have infinite resistance. And this is going to come as a shock to a lot of people used to working at certain frequencies. But although the actual DC or leakage resistance is typically quite large, it's still not infinite resistance. So in addition to the DC resistance, there's an AC loss, which can be represented as a resistance. And the AC loss corresponds to the microscopic frictional loss, which arises from polarization of a charge as the voltage changes. Now this loss translates to heat, and it's very important to consider when using capacitors for high current applications, such as power supplies. If too much AC passes through the capacitor, it will heat up, limiting its useful lifetime. And this is the reason why that manufacturers will often specify what they call an ESR, or an equivalent series resistance, which lumps all the resistances together of that particular capacitor. So ceramic capacitors, for example, typically have low ESRs, but they require too large a volume to be practical for large capacitance values. So in other words, if you needed it to be a large capacitance value, it would have to be the size of like a soda can or something in the real world. Aluminum electrolytic and tantalum electrolytic capacitors are available in large capacitance values. The trade-off there, and there usually always is one, is that these do have higher ESRs. Now, of these two types, the tantalum electrolytic capacitors have the lower of the two. So just something to be considering when you're looking at both your on-chip design and your probe, as we talk about later. If these have large capacitance values, just be aware that they're essentially going to become heat generators. And the degree to which they become heat generators is specified in under the ESR value typically given by the manufacturer. So for high frequency design, the parasitic series inductance actually poses the largest problem, right? The inductance creates a resonant frequency, as we see here at the inverse of the square root of L times C, or the inductance times the capacitance. So most of you are familiar with the pretty standard equation for calculating resonant frequency. And above this frequency, the impedance of the capacitor increases. So in other words, the component starts to act like an inductor above the resonant point. If you start to see that happening, or if you model it and see that happening, there's really two approaches that you can do to increase the resonant frequency. That's to reduce the parasitic inductance, or use a smaller series, or smaller value of capacitance. Right. So that's kind of some things to be mindful of with capacitors. If we move on to the next slide, we can talk a little about the true inductor. So we've talked about the resistor and the capacitor, and now let's talk a little about kind of the true inductor and what happens with an inductor at higher frequencies. So in general, inductors are even more problematic than capacitors. I hate to be the bearer of bad news here, but this is often the case. And we see again here the circuit model for a real inductor. And the parasitic elements that we find in an inductor are the resistance within the leads and the wire itself of the inductor itself. And the other parasitic element is the capacitance between the leads and between the loops of wire. Then, of course, there's even the equivalent resistance corresponding to core losses. And that's assuming if the inductor uses a ferromagnetic core. So if it does, it introduces yet a third parasitic element, again, which is the equivalent resistance corresponding to that core loss. So the parasitic capacitance forms a resonant circuit with the inductance at this resonant frequency. So above this resonant frequency of the inductor, the impedance of the inductor decreases with frequency. In other words, the component starts to act like a capacitor above the resonant point. And this is the kind of thing that makes microwave engineering so interesting, in my opinion. The fact that things start to act very differently, or radically differently as you go across in frequency and trying to match for that given frequency. And this is kind of the puzzle that many of us microwave engineers struggle with or enjoy, in my case, dealing with playing with things like this on a Smith chart and making everything work just right. So, as I mentioned, though, there above this resonant frequency, this inductor can actually begin to act above like a capacitor. And there are two options, again, to increase the resonant frequency, similar to what I talked about with the capacitor. So you can change the resonant frequency point primarily by reducing the parasitic capacitance, or choosing an inductor that's specified with a lower parasitic capacitance, or using a smaller value of inductance. So you kind of start to see a theme emerging here that at higher frequencies, utilizing components of high values, be it capacitive values, resistance values, or inductance values, begins to become less and less practical. While it's certainly still possible, it certainly adds a level of complication and some things that need to be considered at higher frequencies. So if the inductor contains a ferromagnetic core, the core losses will also limit frequency response. And that's really a lot of what we're talking about here, is how is this component going to respond or react over a given set of frequencies. So very seldom is it ever that a device is only going to be operating at a fixed frequency with little or no bandwidth associated with it. Typically, a component in a design needs to be designed such that it can handle some range of frequencies, and especially as those frequencies get up above the near or above the resonant point of that particular component, then things get really interesting. So if you have a inductor, in this case, that has a ferromagnetic core, the core losses will limit frequency response. And the core losses arise primarily due to the hysteresis. Losses from the eddy current within the core. And this situation is complicated by the fact that hysteresis losses are nonlinear and that the current losses increase with frequency. So it gets really challenging to kind of model these things out if you're doing software modeling, because again, the hysteresis losses isn't a nice linear response, and it will vary significantly according to kind of the design of the component. So this is where measurement, there's really no replacement for measurement. Simulation is great. It's a great tool. I use it regularly, and I encourage my clients to use it. But at the end of the day, you really need to get in there and make some measurements and see how well they correlate with your simulation, and kind of feed that in as the baseline for any future simulation software or exercise. And, just one more thing on the true inductors. The limitation, there's also a limitation to how much current they can carry. So I've gone in with some folks and trying to help them with kind of ESD chokes on their power supplies and that kind of thing. And one of the things we really have to be careful of when we start to do that is the current that we're trying to run through an inductor. So this limitation stems from the resistance of the conductor that actually make up the component and its leads as well. So inductors, especially again with ferromagnetic cores, are further limited in that the current must be kept below the saturation level for the device to operate properly. And typically this saturation level is specified by the manufacturer. So a number of things to consider when using inductors in your design, or we'll mention later, kind of in the probes or what have you. Anything that's going to be either utilized in your design or going to touch down and test your design is going to affect the response, the frequency response of your signal. right? So that covers the true inductor. So now I'd like to kind of talk about the fact that there are a number of applications for what we just reviewed. So if you talk about parasitic capacitances and inductances, then there's a lot of ways that you can apply that theory. It can be used in impedance matching and properly utilizing RF and ESD chokes in a circuit design, as well as selecting the optimal transmission line, be it on a PCB board, circuit design, or even you can utilize these kinds of theory for just determining the type of transmission line you want to use to run up a base station or what have you. So there are a lot of different areas that you can focus on to talk about how to apply this kind of theory, but I decided today to focus on another useful application, which is oscilloscope probing. And quite honestly, I'm doing that because I see so many problems with people doing it properly, or not doing it properly actually, especially at high frequencies, with digital buses and probing on high-speed digital circuitry. So accurately measuring digital waveforms with oscilloscopes really becomes increasingly challenging as edge speeds become faster. So probing any circuit for the purpose of making a measurement will always change its operation. And this is one of the first things that I get people on board with when I go in and talk to them is you have to understand, I'm going to definitely try to help you optimize your probing, but the minute you touch a probe tip down on your design or solder it on there, what have you, you are going to have some kind of effect or impact on its operation and on its frequency response. So that kind of has to be factored into the data that you're collecting as well. So especially when you're measuring waveforms with a high frequency content, this is even more applicable. Extremely small parasitic elements added to the probe circuit often greatly distort the signal being measured. This is where you really need to understand the effective circuit of your probe and think about which probe you're going to use and how you're going to use it. So the most significant factor that contributes to waveform distortion is the probe loading. The impedance in the probe to ground forms a voltage divider, which attenuates the measured signal, and this attenuation typically increases as we go up in frequency. And if the impedances were purely resistive, this effect could be easily compensated for by applying a scalar multiplier to the measured waveform amplifier, to the measured amplitude. So you could simply make your measurement, apply some simple correction algorithm to it or what have you, in something as simple as Excel, and get the corrected output data. However, the reactive portions of the circuit's source impedance and the measurement probe themselves create a frequency-dependent attenuation. And this can't really effectively be corrected, again, because it doesn't follow necessarily a straightforward algorithm or behavioral pattern. So as the frequency content of the signal being measured increases with these higher clock speeds, faster rising edges, even the most minute parasitic capacitance and inductance will impart significant attenuation. And that will basically really distort the appearance of the measured waveform. So trying to really get in there and measure the true appearance of your waveform and try to minimize the effect of the impedance and the capacitance values of your probe is what we're going to talk about here in the next few slides. Starting with the next slide here, where we'll talk about, on slide 8, one probing consideration example. Right? So here's an example. And we see that here what we're trying to do is probe a fast digital signal with a 1 nanosecond transition time using a high quality passive probe. And so not some probe that was made in your garage or whatever. Maybe you've got a great lab set up there, but I'm going to assume here that you bought this and it's been manufactured well and it is a high quality probe. So the input impedance of these probes is generally on the order of 1 mega ohm. So here we are probing. It's a passive probe, and passive probes generally have a fairly high impedance on the order of about 1 mega ohm, in parallel with about a 10 picofarad capacitor. So if the source impedance of the circuit being tested is 30 ohms, as is here in our example, the 1 mega ohm resistive component of the probe creates virtually no DC attenuation. However, the effect of the capacitance is significant. Using the basic rule to translate rise time into frequencies, so we say we got a 1 nanosecond rise time. If we convert that, take the inverse of that, we get into approximately 350 megahertz of spectral component here. And the capacitive reactance at 10 picofarads at 350 megahertz is 45 ohms. So what we're saying is that during the 1 nanosecond transition, the impedance of the lower leg of the voltage divider would be a 45 ohms rather than 1 mega ohm. And that would attenuate your signal by about 40%. So this is where things of this nature, where all of a sudden you're expecting to see a signal at one amplitude, and you're seeing it attenuated significantly, in this case by 40%, as you probe these fast rising signals on the order, in this case, of 1 nanosecond. It can be a real significant difference in what you measure versus what you would expect to measure. So how do we adjust that? Or how do we address that? So if we move on to the next slide here, we see that a lot of folks say, well, you just use an active probe, right? If you want to decrease your capacitance and you want to be able to have that high input resistance, so you don't load down your circuit. The answer is just simply to get an active probe, and I would say, yeah, maybe that's the case, depending on if your frequency is not too high. You still have to be considerate of that. Then also, one of the biggest fallbacks of an active probe is the dynamic range. You have to consider that. And also the voltage input, since it is an active probe, so it's actually amplifying the signal. There's a little FET typically in there, a FET-based amplifier. So you have to be mindful of the voltages that you put into this probe and any of the electrostatic discharge that might be going across it. I've definitely had a lot of clients blowing out probes. And then lastly is if you have enough dollars. Now hopefully if you've made a significant investment in your oscilloscopes and you're trying to develop effectively design a good device, a good transceiver or what have you, or a good digital bus, it's worth it to spend a few extra dollars for a good probe that's going to do what you want and give you effective measurements. I mean, it doesn't make sense to spend on the order of even $10 or $15 or $20,000 on an oscilloscope, or even a few thousand, I would argue, and then save yourself a few $100s on a probe but not be able to make effective measurements. So yes, of course, active probes are more expensive, but if it turns out that's what you need, then that's what you have to do. Otherwise, you just have a big paperweight in your oscilloscope and not really take effective measurements. So I mentioned in my last slide about this 40% error, and this is obviously something that we can't generally live with. Most folks don't want to tolerate 40% measurement error or greater. So if they're measuring high-speed circuits, for example, like the one we mentioned earlier, they might go ahead and move to an active probe. And as I mentioned, these active probes usually use a small FET-based amplifier that are mounted directly within the probe head. And then by doing this, the probes are able to obtain exceptionally low parasitic capacitance and a high DC resistance. So it's pretty common to see capacitance on the order of 1 picofarad or less, with 1 mega ohm or more on an active probe. And again, all this data would be given on the data sheet from the manufacturer. So a typical input of 1 picofarad capacitance for an active probe represents easily a 10-fold improvement over the high-quality passive probe. If you remember our passive probe, we had about a 10 picofarad input capacitance. However, even at 1 picofarad, the active probe can still present too much loading in very fast circuits. So if we looked at a 3.5 gigahertz signal or spectral content, a 1 picofarad active probe loads that signal with the same 45 ohm capacitive reactance as the 10 picofarad capacitive probe, call it at 350 megahertz. So the same problem that you had with your passive probe at 350 megahertz, so you move up to an active probe, and now maybe you're probing 3.5 gig. Now you're going to still find that 40 or that 45 ohm capacitive reactance. This is going to be causing you a problem. So again, you always have to be mindful of what frequencies that you're probing, and can take that into account. Now, even at lower frequencies, as I mentioned, there's some different disadvantages. These are what's been keeping most engineers and technicians from just completely replacing passive probes. So the question is, well, if they're so great, why don't we just always use passive? Why don't we always just use active probes and just do away with passive probes altogether? And there's a few reasons for that. One, of course, as I mentioned, is they're several times more expensive than passive probes. So while it certainly makes sense to lay out that kind of money or that capital if you need that to successfully manufacture or measure your device, in cases where passive probes do the job equally as well, then of course why spend the extra money? Another thing is that they, of course, require power. By the term active probes, meaning there's an amplifier on board, so you usually have to find some kind of power source. And a lot of oscilloscope manufacturers will supply you that on the oscilloscope itself. You'll plug the probe into some type of a voltage supply on the oscilloscope itself. But just something to be aware of, that they do require power. They have a limited dynamic range, and this is probably the number one reason, aside from its sensitivity to voltage and ESD and blowing it up is a very expensive proposition, but also the fact that it has a very limited dynamic range. It could be even as low as in the area of 3 to 5 volts. So if you're trying to measure a signal that could be having significantly more voltage swing than that, or values that go outside of a 3 to 5 volt window, it can be a real challenge to do that with an active probe. And as I mentioned, of course, yes, overvoltage and ESD is a consideration as well. Now, one of the things you can do to overcome the limited dynamic range is a lot of these active probes will allow you to introduce an offset voltage. So you still have a limited dynamic range. You still have this kind of window, if you will, of ranges of maybe 3 to 5 volts that you can measure over, but you can adjust that window and try to center it around what you would expect to be the nominal value of the voltage that you're measuring. So, for example, you can measure 0 to 5 volts. Maybe you can put your center point voltages down to where you can measure from 0 to 5 instead of from minus 2.5 to plus 2.5 or something like that. If you know you're going to have a pretty much a voltage swinging in that window. So that's one option that you can use if you decide to go with an active probe. All right. So on the next slide, I'll introduce this concept of a relatively unknown type of passive probe. And I think they're starting to gain more popularity, but there's still a lot of clients I might have noticed that aren't even aware that these exist or that they would be practical to use in their measurement application. And these are called ZO probes. And these are also passive probes, but they're known by several names actually: transmission line probe, low capacitance probe, low impedance probe, or as I mentioned, ZO or probe. And regardless of what they are called, they all work under the same principle. So these probes are a specialized type of low capacitance passive probes used in low impedance, very high frequency circuits. They're very similar in design to ordinary passive probes like we showed earlier, but they are designed to connect to the oscilloscopes with 50 ohm input impedance rather than 1 mega ohm. So this means basically we'd have to set typically the impedance on an oscilloscope is 1 mega ohm, but it's often switched, or at least every oscilloscope I've ever seen actually allows you to switch between 1 mega ohm and 50 ohms. So if you utilize this type of probe, you would need to set your oscilloscope to 50 ohm termination so that you have a completely match between the cable and the input of the oscilloscope. So over a specified operating range of frequencies, the input impedance of a transmission line will appear purely resistive, so in this case 50 ohm. And lacking the capacitive component of the lower leg of the attenuator, no shunting capacitance is required across the tip resistor to compensate the divider. So what this means is that in theory at least, such a probe would have zero input capacitance. So you remember I talked earlier about the importance of input capacitance and how even at picofarad or less, as you get up in high frequencies, like we gave the example of 350 megahertz and 3.5 gigahertz, even tiny input capacitance values can have a dramatic effect on the attenuation of your signal at high frequencies. So if you have a probe that at least theoretically has zero input capacitance, of course, you now have reduced that as a factor in your attenuation of your measurement. Although, of course, in real life probes have a very small capacitance, this is primarily resulting from the proximity of the ground connection in relation to the tip. But again, this capacitance is still very low, maybe 2.2 picofarads or less. So again, significantly less values than the 10 picofarads or even the 1 picofarad that we mentioned for the passive and even the active probes. So the only real potential downside to using this type of probe, and by the way, I don't sell or get any benefit if whatever probe you decide to go with. I'm not a probe manufacturer or probe seller. These are just one of the probes that I often find work really well for my clients especially who are doing high-speed digital design and testing. And one of the reasons that they often decide not to utilize this type of a probe, and for those who are even aware of it, I hear, well, but they have a lower input resistance. I'm concerned about loading my circuit. If you have a low input resistance on your probe, then you might not be able to drive it hard enough to actually see your signal or to get an accurate measurement on it. And I understand what they're saying. A divide by 10 probe, for example, has an input resistance of about 500 ohms. And a divide by 20 probe weighs in at around 1 kilo ohms. And this low input resistance, again, is why many designers have avoided using them in the past. But with the increasing speed of these modern digital systems, when we start to see them switching at much higher frequencies and so on, the transmission line probe, I think, deserves kind of a second look or more serious consideration. Most modern high-speed digital circuits are not impacted by this resistive loading because the voltage swings tend to be lower and the ICs can drive lower impedance loads. Especially here in just the last 3 to 4 years, I've seen this more and more becoming the case. So in many cases, the 1 kilo ohm may not adversely affect the operation of the transmission line buses, which are becoming more common again in these modern digital communications. So it's worth having a look at if you're using a 1 kilo ohm load, if your transmission line bus or the line that you're trying to measure at a high-speed circuit, in many cases nowadays can successfully drive a 1 kilo ohm load. And if that's the case, then CO probes are definitely something worth a look, and getting a hold of one or something and just giving it a shot. So as I mentioned here, my little smiley face and frowny face chart, the smiley face is, is the low capacitance. So this means improved flatness, improved frequency response of your measurements without significant attenuation, which will increase as a function of frequency. The frowny face side is that there is a low resistance on the order of 1 kilo ohm or less, depending on what kind of divide by setting you got going on. Will this cause resistive loading? I put a question mark. Maybe yes, maybe no. It really kind of depends, but it's worth a look and worth something to think about. So, in the next slide there, and kind of in summary, we've talked about kind of the fundamentals of parasitic, the effects of these kind of parasitic occurrences in both impedance and capacitance and reactance, and how that applies to using probes and why probes are designed the way they are, and what to think about when you're selecting and using a probe. And lastly, I just want to say, so now maybe you've got the right probe. I say, now don't mess it up. A lot of people will get a really great probe, lay out a significant investment in some cases to get a number of these probes, especially active probes. And if you do that, if you get these high bandwidth performance probes, it's really important to avoid introducing the parasitic reactive elements into the input connections. The whole reason that you bought this probe to start out with. So again, it's amazing to me how often I don't feel alone if you're in this case, but I certainly have gone into clients before and found that they've laid out and have these really nice, super high bandwidth probes, very nice flatness, super low capacitance, in some cases, nice high resistance, so you're able to drive them. But then they do things like put on 10 centimeter ground leads and attach these miniature SMD lead clips with 5 centimeters of extension and stuff in front of them. So and it completely ruins the whole purpose of why they bought these probes in the first place. So again, just avoid doing these types of things. Anything that will introduce, again, a parasitic reactive element to the input connection, such as using these extenders and these really long leads. Keep here. If you can avoid it, by all means do. But if you have to use ground leads, use short ground leads. Use the shortest lead clips and try to avoid extensions and like that. So the ultimate goal at the end of the day is to get the bare probe, the bare circuit, with as little in between as possible in order to avoid these parasitic responses. So if by doing that, you'll avoid kind of having this devastating effect on your waveform fidelity and possibly alter the operation of your circuit and make better measurements. So hopefully now you have a little better clue about probing, what types of probes, what are their advantages and disadvantages, selecting one, things to be mindful of in utilizing them when you're measuring, and then also some of the practices to avoid when you actually do now have selected your probe and are using it to measure your circuit. And that's what I've got for you for today. So if you have any questions, or if you're interested in the getting a webinar or some additional information or training on voltage probing and general measurements, you can reach me at my company. My name is Louis Parker, LOUISPARKER, and you can reach me at Louis Parker, all one word, at T as in Tom and ANDM as in Mary, consult.com. Louis Parker at tnmconsult.com. Or you can go to our website, www.tnmconsult.com. Thanks.
That's it for your first iChan interview. And I hope you like the format. And if you would have a suggestion for any topic you'd like to see us do on a future episode, send us an email at suggestions@learningmeasure.tv. If you have a question, any question at all, send us an email at questions@learningmeasure.tv. And if you have if you want to be on the podcast, do your own interview, send us an interview at vendors@learningmeasure.tv. That's it for this week. We'll see you next time.